Okay, it's okay, very good. So, welcome everybody to this set of Gyan lectures, the course on advanced photon sources from synchrotrons to free electron lasers. We are very delighted to bring to you this new, advanced, and modern topic on synchrotrons and free electron lasers, particularly in the X-ray domain. As you may have read about it from the course brochure, the title, and possibly asked your favorite AI search engine about what this is. Uh, Essentially, these are the most modern advanced photon sources in the short wavelength region. Clearly, your question is going to be what are these? How do they operate? What do we apply these to? And what good are they for in terms of science, technology, and more? So, to answer these questions, we have a very eminent expert who is a practitioner in this field for a substantial amount of time, and in this case, also my uh, long-standing collaborator, Professor Marcel Modrisch. So he is currently and recently with the University of Kassel in Germany, where he is setting up an advanced lab in this particular science. Earlier, he spent a substantial piece of his time as a faculty member at the University of Aarhus in Denmark, in the city of Aarhus, Aarhus University, where he established a special beamline for looking at nanoscale matter, helium nanodroplets, again, confined matter in terms of water droplets and others with X-ray synchrotron radiation with advanced forms of spectroscopy like photoelectron, photoion coincidence spectroscopy, and more. And beyond his own laboratory, he has done some fascinating research using both synchrotrons and X-ray free electron lasers, particularly X-ray free electron lasers from the perspective of doing single shot diffractive imaging, that is getting a whole diffraction pattern using a single femtosecond X-ray pulse as only X-ray free electron lasers can do so far, and that is really the state of the art of X-ray photon science. He is also a very well-known expert in the community that works on quantum fluid clusters or helium nanodroplets and has a long-standing expertise in studying a variety of systems in or on this particular exotic nanoscale superfluid. But he has also worked on cold atoms and several other aspects of spectroscopy. So, an A spectroscopist. Therefore, it would only be appropriate that now I hand over the floor to Professor Modrish. Please take over and let's begin this Gyan course on advanced photon sources and synchrotrons. But just a 30 seconds more for the students who have joined us while I took the opportunity to welcome you. Please stay alert for communication by email and on the WhatsApp group. We have a WhatsApp group for quick communication. We really intend this to only serve the thing for announcements, so that we are able to quickly catch up on the details. So we have students all the way from here in India to Germany, Prague, Freiburg, and the Czech Prague and Czech Republic, of course, and so on. So we'll try our best to synchronize all these events. So for students, all you need to do is to listen to these lectures, pretend that you are in the same lecture hall as Professor Modric, and do this. I mean, take your notes down or uh, keep questions ready for when we can answer them. We would like to make this as interactive as possible, however, leaving time for a little bit of monologue in between just to establish concepts and equations. We have time for the lecture. We also have some times for tutorials. We have announced the lecture times for you. We will intersperse them with tutorials. The course is intended to go on within this month, pre and post Christmas. We know that this is time not only for learning but also for some fun. So we'll stick to the schedule. Though formally we finish on December 31st, we will also extend a little bit informally into the month of January, but that is all on a need to basis. So we have lectures. We also have planned some hands-on activities with the help of Professor Mudge's students and my students. So welcome again to this course, and it's going to be fun, trust me. And now for real, Masal, it's yours.
Yeah, thanks, Shiva, for this very kind introduction. So, you have already said some words about me. Let me just maybe complement the answering the question, who am I? Just so you know who you will be listening to. So, yeah, as Shiva has mentioned, I have been doing spectroscopy of molecules and nanoclusters um, for quite some while, and a particular focus is on superfluid helium nanodroplets. So certainly in the course of these few lectures, you will see results on helium nanodroplets several times. This is really, let's say, our toy system that we have been studying and poking in various ways over the years. Yes, so as Shiva mentioned, I'm a frequent user of mostly XUV synchrotron facilities, also free electron lasers, and more recently HHG facilities. HHG stands for high harmonic generation, which is a laser-based technique. We will talk about this shortly. And so this usually you find in laser labs, but since recently HHG sources are also provided on a facility basis where any users, including users from India, can apply for beam time and also perform experiments without the need of maintaining large-scale laser systems and expensive equipment themselves. So the synchrotron sources that I'm mostly using and where I'll be showing some examples from is Astrid 2 synchrotron. That's a small-scale synchrotron based in Aarhus in Denmark. Then together with Shiva, we have been doing many experiments at the Elettra synchrotron in Trieste in Italy over many years now. We are doing experiments at Soleil in France, Max 4 in Sweden, free electron lasers, Fermi in Trieste. There's two free electron laser facilities in Hamburg, in Germany, not so far away from here, Flash and XFEL. Particular XFEL I will certainly show in more detail. And soon also SwissFEL, which is yet another X-ray FEL in Europe. And the HHG facility is that we are using as Eli beamlines. I will also show a few results from those experiments. I am currently representative of the SQS instrument. That's one of the end stations of the European XFEL, where I'm representative of the user organization executive committee. Yeah, I have published more than 100 papers, most of them about synchrotron and FEL related experiments. You can look up some papers if you're interested. And as Shiva mentioned, currently I'm a full professor at University of Kassel in Germany, only since very recently, actually. Before that, I've spent 8 years at the Aarhus University in Denmark, which is a special university in the sense that it has its own synchrotron, Astrid 2, this one here. So I will show a few. I will introduce this synchrotron certainly. Before that, I was adjunct in Freiburg in southern Germany. I did a postdoc in France and my PhD and studies in Heidelberg. And so my PhD thesis I did at the Institute for Nuclear Physics, Max Planck Institute for Nuclear Physics. And that's actually where Shiva and I met and did our first joint experiments a long time ago already. And yeah, my email is here. Please don't hesitate to contact me if you have any questions or any comments. Okay, so let me start with just let's say, thought experiment. So imagine we could build a light source, the ultimate light source. So what would the ultimate light source be? Well, certainly in terms of wavelength or color, it should be a light source that is tunable over essentially the whole electromagnetic spectrum, from infrared up to X-ray range. That would be the ideal light source, right? Choose any wavelength you want to address specific molecular vibrations, atomic transitions, or even core ionize or atoms, or even excite nuclei in the hard X-ray. If we had a light source that covers this entire range, that would be just perfect. What else should the ultimate light source have as properties? It should possibly be extremely bright so that we can drive even the weakest transitions, or we could also drive nonlinear processes where you need high intensity, even up in the X-ray range. And extremely bright, I mean, the almost the most extreme intensity you can think of would be an intensity higher than even the atomic unit of intensity, which is defined as epsilon naught c half times the atomic unit of electric field square. Yeah, intensity depends on the electric field square. And the atomic unit of electric field, that's just the electric field that uh, binds the electron to the proton in the hydrogen atom. So that's given by this simple Coulomb term. And this atomic unit of intensity is on the order of 10 to the 16 watts per square centimeter. So any intensity larger than that would obviously just ionize, like rip apart electrons from atomic nuclei, because the electric field of the light pulse would be stronger than the binding electric field inside the atom. Um, yeah, another property that might be very desirable is extremely short pulses to perform not only like static spectroscopy by like tuning the photon energy over certain absorption resonances, but even perform time-resolved experiments where obviously short pulses are needed. Like in the simplest scheme, very short pulse would initiate some very fast dynamics, and then a second pulse would probe the dynamics, which is called the pump probe scheme. And if we like want to reach down to the shortest time scales, which is given by the motion of electrons in atoms, then the figure of merit would be the Bohr, the period of the Bohr orbit, like how long does it take for the electron in the ground state of the hydrogen atom to orbit around once, which is 152 attoseconds. Yeah, this 10 to the minus 18 seconds is an attosecond. So that sets the time scale for electronic motion. And the ideal light source should be coherent. And coherent means, or spatially coherent means that it can be focused down to very small spot sizes, basically limited only by diffraction. And if now we had a light source in the X-ray range with very short wavelength, then in principle, we could obtain extremely small focus spot sizes of less than 1 micrometer, which again would provide us very high intensities. Coherence would also enable us to do what is called coherent diffraction. Yeah, that the light pulse can be diffracted of an extended object, and interference would happen at different places inside the object, so that an coherent diffraction image can be recorded, from which we could calculate back the structure of the object. Coherence could enable coherent control schemes, meaning driving quantum processes in an atom or in a molecule in a coherent way. Coherence is the prerequisite for holography, for lithography, and many other like optical methods. So this would be the ultimate light source. And the question is, does it exist? Well, here on I haven't talked about the figure to the right. This beam that you see coming out of a sophisticated beamline here and shining bluish as it propagates through air, this is actually pretty much such an ultimate beam of light, which has been realized. So only since rather recently, you can find this image on the website of the European XFEL. So yeah, X-ray free electron lasers. This is the light sources that pretty much come as close as possible to this ultimate light source that I've just described. And it's actually started, so these X-ray free electron lasers started out with the LCLS, that's free X-ray, the first free electron laser, X-ray free electron laser that was built in Stanford in the United States. Of course, such a light source comes at a huge price. Yeah, so just the building cost of the first phase of LCLS one was almost $500 million US dollars. Nowadays, there's another one in Japan called Sakla. This was almost as expensive, 300 million US dollars. And since about 10 years or so, also in Europe, there is a very powerful X-ray free electron laser, which is called the European XFEL. And yeah, as often in Europe, everything is even more expensive than in the rest of the world. So here the cost was about 1.4 billion US dollars. So these are, of course, enormous investments, but as I tried to explain, these light sources then obviously come closest to the ultimate light source that we may imagine. And before I forget, there is a homework until tomorrow, until the next lecture. Homework is, please watch this YouTube video. We could actually post the link in the chat maybe later on. This is a very nice introduction to how X-ray free electron laser works, in particular the one in Hamburg, the European XFEL. Okay, maybe before getting started with more details, this is the brief overview of the outline as planned so far. So today and tomorrow, I will be giving an introduction first to lasers, because free electron lasers are actually specific type of a laser, but we should recap some of the laser physics. And I will also show a few other types of X-ray sources before then diving into synchrotrons and XFELs. Then tomorrow it will be mostly on the basics and applications of synchrotrons. Next week we will talk more about then the free electron laser principle, and in particular the working principle of XFELs. And so next week there should also be numerical simulations to be done as tutorials. So we are still working on that, but it looks very promising, would be fun. Then the week after, we will talk about some applications of XFELs. One of the most prominent ones is coherent diffraction imaging of nanostructures. And there will also be some tutorials on that topic. Then later on, shortly before Christmas, let's see how it goes. We will then talk more about applications of these XFEL beams in the beam lines and what techniques are being used. And then probably early next year, I will review a few very recent developments and also some hybrid approaches that go beyond XFEL or combine XFEL and synchrotron radiation with other types of radiation. So this is also very new developments. But yeah, today more about an introduction and a recap of laser basics. Then I will present some XUV and X-ray sources that are not directly synchrotron related, but still important and interesting, let's say, competing methods. And then I come to a more formal introduction to synchrotron radiation, and we will probably continue with that tomorrow. Yeah, just as Shiva mentioned, active participation is highly desired. So please ask questions anytime you like. It's very nice to have some dialogue, even though it's online, but let's try to keep it lively. And
So you're not getting Wi-Fi, huh? You're not getting.
can I go on? Okay, I'll go on.
Marcel, sorry, that was unintentional. You edited it.
Okay, so it's not on my end. That's good.
No, no.
Yeah. So before, as an introduction, let's have a look at the electromagnetic spectrum and see where laser radiation is available. So since the 1960s, so 1960 actually was the date of birth of laser physics, we can say, at least in experiment, in the real world, not only in theory. And with the invention of the ruby laser by Theodore Mayman, as probably you have all heard about. And since then, lasers have been developed that cover pretty much the entire electromagnetic range, reaching from mid-infrared, yeah, the CO2 laser being probably the most important infrared laser, which is still being used very successfully also for even in industrial applications. We will see some examples later on. Yeah, going via erbium, YAG, so different solid state laser systems. The helium neon laser is probably familiar to all of you. Neodymium YAG. Actually, this is the second harmonic at 532, which is in the visible, and then reaching up to the UV, where argon fluoride or even fluorine lasers are probably the lasers with the shortest wavelength that can directly be produced by lasers, which is ultraviolet radiation. But the electromagnetic spectrum, of course, extends much further out into the short wavelength range, yeah, into the extreme ultraviolet. Into the extreme ultraviolet range, soft X-ray and even hard X-ray. And X-ray regime, of course, is very important for science, also for technology. Just to name a few, prominent examples: structural biology, material science, physics and chemistry in general. So X-rays are being or have been used in these sciences for a long time, but there is no laser that directly produces EUV up to X-ray radiation, at least until 2009, when the first X-ray free electron laser was built, which was the LCLS in Stanford. Yeah, so I mean, if we had now readily available X-ray lasers, what could we do with those? Well, what is always mentioned in the first place is biology, structural biology. So because X-rays until today are the most important light sources that actually have been used for resolving the structure of proteins, not coherent laser X-ray radiation, but just incoherent X-rays, but still. If we had now coherent ultra-short X-ray pulses, then we could actually perform time-resolved experiments and, for example, watch how proteins fold and change their structure and develop function. That would be an exciting topic. Another very important field is real-time observation of chemical reactions. For example, this photocatalysis reaction where water is split by sunlight using some photocatalyst, which is, of course, an immensely important field of research. But also, owing to the extremely high intensity of X-ray lasers, that if they were readily available, would be the study of what is called warm dense matter, which is matter under extreme conditions of high density and high temperature, as, for example, the matter that is present in the core of giant gas planets. So this would allow us to study the properties of matter in regimes that are so far not available or not accessible on Earth. And owing to the extremely high photon energy, so going to hard X-rays, then it should be possible to even measure nuclear transition, like nuclear atomic transitions. For example, those you might have heard in thorium. Only a few years ago, it has been found that there are nuclear transitions even down to the extreme ultraviolet range, which are extremely narrow, so very well suited for high precision measurements, including atomic clock schemes, which would require XUV or X-ray narrowband radiation to do such spectroscopic measurements. Okay, but so this is the motivation and the justification for these enormous investments that are being done for building this kind of lasers. But before coming to these more sophisticated laser systems, let's recap a bit what a laser is and how the basic concepts of laser physics can be implemented in these X-ray regimes, and what limitations and problems we might encounter. So a laser in principle, in brief terms, is shown on the left-hand side. So it consists of, first of all, a pump. We need an energy source that energizes an active medium. So we need the active medium, which has the property of amplifying and coherently amplifying light. And the process that is at the basis of coherent amplification of light is stimulated emission. So the active medium needs to provide an optical or X-ray transition at exactly the right wavelength to amplify the light. And then conventional laser needs an optical resonator, which is indicated by these two vertical rectangles here, labeled HR for high reflective mirror, and OC is labeled OC for output coupling mirror. So one mirror solely reflects the light, and the other one reflects the light and also transmits part of it, such that a laser beam can be outcoupled out of this resonator, which is also called an optical cavity. And this basic laser concept can be, that's really, I always realize that this is really exceptional, that such a simple basic concept can actually be realized in many various ways. For example, what everybody knows is the helium neon laser, which is this rather simple realization of the laser concept, where the active medium is provided by an electrical discharge in a gas. And this gas tube is filled with a mixture of helium and neon, and by electron collisions, neon atoms are excited into highly excited states, which then can transfer their excitation energy into the light field by stimulated emission. And in the helium neon laser, we actually have two mirrors, left and right, to close the cavity, and the output coupling mirror then outcouples a laser beam. But the laser principle can also be implemented in a sub-millimeter small semiconductor chip, like the one that is encapsulated in this laser diode. So here, the laser medium consists of a few hundred micrometer thick semiconductor layer, which is pumped by just injecting current into the semiconductor structure, and transitions from the conduction band to the valence band then drive the stimulated emission and the amplification of the light. But the laser principle can also be realized by a liquid. Yeah, this here shows a glass cuvette that contains a liquid dye solution. So this is a solution containing organic molecules, dye molecules, which have the property of particularly efficiently absorbing and emitting light. And because we need a pump, we have to optically excite these molecules. There's a laser resonator for the feedback, and then this liquid can act as a laser medium, an active medium. And yeah, well, the main topic of this whole course, yeah, the laser principle can even be implemented in a huge accelerator and undulator structure, which extends over many kilometers, even like shown here from this airborne view of the city of Hamburg. So this 3.5 kilometer long structure basically acts as a laser almost in the same way as this sub-millimeter small semiconductor chip encapsulated in this diode laser. Okay, so that's the laser principle that you probably were familiar with already. So how can we now transfer this concept into the X-ray regime? It turns out that actually all these three elements, now the pump, the active medium, and the optical feedback in a cavity, all these three elements are very hard to transfer into the X-ray regime. And like now in the course of probably today and tomorrow's lecture, we will look a little bit more into why this is. What makes it so hard to build an X-ray laser according to this basic concept. First of all, let's recall that laser is actually an acronym. It's an abbreviation that stands for light amplification by stimulated emission of radiation. And in particular, stimulated emission is the key term here. So stimulated emission is the process that amplifies radiation. And stimulated emission is one of the three basic light matter interaction processes that you probably know. One process is absorption, which is actually also a stimulated process. We shine in with one photon to excite an atom or a molecule or a solid state system from the ground state into an excited state. This is a stimulated process, just as basically the equivalent process, just going the other way around, is stimulated emission. We start out with an excited system, for example, neon atoms in excited state, then come with an extra photon, and this extra photon then de-excites the system. And by this stimulated emission process produces a second photon, which has these exceptional properties of having exactly the same frequency and even the same phase as the driving first photon. And so this is really the secret or the basis of the laser process, that by stimulated emission, we coherently amplify the radiation. Of course, there is also what is called spontaneous emission. So an excited system in an excited state will never stay there forever. It will always decay after some time by emitting a photon and then fall back into the ground state. And this spontaneous emission, that's the light source that we are most familiar with. I mean, if you think about light bulbs in, like for example, so the sodium, these orange light bulbs that are still being used for illuminating the streets, their sodium atoms are excited and decay by spontaneous emission to emit light. So that's what we mostly know. And that spontaneous emission is actually the enemy of the laser process, because spontaneous emission happens spontaneously. So there is no phase correlation of one photon with the other. This is completely incoherent emission. And that is detrimental if we aim for producing coherent light by stimulated emission in a laser. So spontaneous emission is the process that we have to fight against and try to minimize. What's the rate of these emission processes? Well, you probably know that spontaneous emission is the rate of spontaneous emission is given by this Einstein A coefficient, which is essentially given by the electric transition dipole moment from the level 2 down to the level 1. That's actually it's to the square, absolute value square of the transition dipole moment. And then there is an important factor, which is the transition frequency, and it scales to the third power of that transition frequency. And then there's just a few fundamental constants. The stimulated processes, so absorption and stimulated emission, actually turns out that they are really exactly equivalent. So they have the same rates up to maybe some degeneracy of the levels, but we will not consider this. So the rate is just given by the Einstein B coefficient, which is equal for absorption and stimulated emission times, of course, it's a stimulated process. So we need a driving field. Well, this is the spectral energy density here in this way of writing it. And the Einstein B coefficient for stimulated emission, again, is given by the transition dipole moment squared. and just a few fundamental constants. So the ratio of spontaneous emission to stimulated emission rate constants, which is called Einstein's relations, is up to some fundamental constants proportional to omega to the power of 3. So the transition frequency to the power of 3. Remember, spontaneous emission, A, is the enemy. That is incoherent emission. What we want is a strong B coefficient or a large ratio of B over A so that stimulated emission dominates. But the problem is it scales as omega to the power of 3. So if you imagine that now we want to scale up our laser frequency from the optical domain, which in terms of photon energies in the visible range, there we are talking about a few electron volt of photon energy up to X-ray, which is in the kilo electron volt. So we would like to scale up by a factor of 1,000 the frequency, a factor of 1,000 to the power of 3. This gives us a factor of 10 to the 9 enhanced spontaneous emission. So that obviously is a huge problem or a huge difficulty if we want to create a laser in the X-ray range that the spontaneous emission is a billion times more probable compared to stimulated emission. So the only way to cope with these extremely high spontaneous emission rates in the X-ray would be then to drive to scale up the drive intensity such that the total rate, which is B times the intensity of the drive field, would still be strong enough or fast enough to beat the spontaneous emission. So that's the challenge. Just to show a few numbers, actually, before the laser was realized, for obvious reasons, a related but simpler scheme was realized, which is called the maser. The maser stands for microwave amplification by stimulated emission of radiation. For example, in the hydrogen atom, a maser can be realized where transitions between hyperfine levels are driven, and the emission wavelength there is the famous 21 centimeter line that you may have heard about also from in astronomy. The 21 centimeter line is very important because matter in space mostly consists of hydrogen, and there is spontaneous emission of on this hyperfine transition to very low extents. But since almost all of the universe consists of hydrogen, then even though the lifetime is very long, yeah, we are talking about a lifetime of 10 to the 7 years, where the lifetime is just the reciprocal Einstein A coefficient. Even with extremely long lifetime, still we see spontaneous emission from outer space just due to the sheer mass of hydrogen present in space. Compared to that, valence excited states of atoms and molecules typically have lifetimes that you probably also know in the range of like maybe 1 to 10 nanoseconds up to milliseconds. Milliseconds, that's quite long lifetimes for valence excited states, but actually some states have forbidden transitions down to the ground state. And in that case, lifetimes can actually be quite long. And actually exactly those forbidden or those long-lived states with forbidden transitions, that's the ones that are very well suited for laser transitions. For example, in the famous neodymium laser, the neodymium 3+ ions, which radiate at the famous 1064 nanometer transition. And those have a lifetime of 230 microseconds, which is long for the standards of electronic excited states, but still much shorter than, of course, these hyperfine states. Now, if we talk about X-rays, and X-rays in atomic physics, you would produce by core excited states. Yeah, for example, exciting an electron out of the 1s core shell of an atom into some free orbital much higher up, then such a core excited state would very, very quickly decay spontaneously by both radiative decay, yeah, by spontaneous emission of the next higher electron falling into the hole in the S shell. But in atoms, actually, there's even more processes possible for core excited states. For example, the Auger process, where an electron fills the hole and another electron is excited or ionized. And all these processes contribute to extremely fast decay rates, which lead then to a lifetime of these core excited states in the range of 1 to 100 femtoseconds. Yeah, femtosecond is 10 to the minus 15 seconds. So compared to microseconds, 10 to the minus 3. Yeah, here we are, sorry, 10 to the minus 6. So we are talking about 1 billion times shorter lifetimes, as expected from this omega to the power of 3 dependence. Yeah, so the only way to beat these extremely short lifetimes by spontaneous emission in order to produce laser radiation by stimulated emission, the only way is that we need extremely high stimulated emission rate, so extremely high intensity to drive the stimulated processes and make the stimulated processes faster than the spontaneous decay. Okay, just a little recap, since we were talking about the hydrogen maser and these extremely long lifetimes for long wavelength transitions. For obvious reasons, since spontaneous emission basically is no issue whatsoever for masers. The maser was built quite some time before the laser. And there's these famous people, mainly Towns, Gordon, Basov, Prokhorov, which who in the 1950s and 60s pioneered the maser principle with hydrogen. Also ammonia molecules are a nice system to drive these hyperfine transitions, or like molecular umbrella transitions, but at very long wavelengths. So this is not light amplification. This is not about lasers. This is microwave and radio frequency amplification, where spontaneous emission is no issue, and it is very easy to reach stimulated emission. Like, just as a recap, for the hydrogen maser, it's actually very simple to build conceptually. Well, actually, it's not so simple if you think about that. In the hydrogen maser, you have the hyperfine split ground state with a transition wavelength of 21 centimeter. And if we now want to amplify the microwave radiation, we somehow have to create an excess of population in the excited state, right? Because we want to drive stimulated emission, and stimulated emission should exceed the absorption, which would be the opposite process. So a prerequisite for amplification is to produce what is called population inversion. Maybe just a short question for as a reminder: how is it possible in this hydrogen system, in the hyperfine split ground state of hydrogen? How is it possible to produce population inversion? Does anybody remember, or anybody have an idea? How can we populate this F equals 2, the spin triplet state, F equals 1, the spin triplet state, how can we populate this upper level with a higher population than the ground level in the hydrogen maser? This is as a recap. Please just speak out if you remember, or if you have just an idea how hydrogen atoms can be populated selectively in the upper hyperfine ground state. What's the method here? Anybody remembers? Or everybody has fallen asleep already? So maybe you remember about lasers. Lasers, their population inversion can be produced by, for example, shining in light, right? The neodymium laser needs to be excited by optical pumping, by shining in with a flash lamp into the crystal. That's a way of energizing the crystal. But how is it with the hydrogen atoms in the hydrogen maser? Can we energize those by shining in light, or can we energize those by driving an injection current like in a laser diode? What's the way of creating the inversion in a hydrogen maser? Nobody remembers. Shiva, do you remember? Maybe that helps to stimulate the discussion. Actually, it's shown here. It is conceptually very easy. Yeah, how about just splitting up the beam, like producing a beam of hydrogen atoms out of a source that's shown to the left, and then by selecting the hydrogen atoms according to their spin states, we can just, by simple magnetic deflection, select out those hydrogen atoms which happen to be thermally populated in the upper hyperfine level. Those selected F equals 1 atoms are then guided into a tuned cavity. So this is just basically a metal box where radiation is reflected back and forth that acts as the optical cavity. Well, it's not optical, it's a microwave cavity. And then the photons that are reflected back into the excited atom ensemble drives the stimulated transitions, and we have maser activity going. Yeah, we just don't have to bother about spontaneous emission at all. The lifetime is by far too long for that. So that's the simplest way of producing population inversion. Just throw away all the bad atoms that are in the bad level. Anyway, that's just a little reminder. Interestingly, so if you are ever asked about do lasers or masers or like these systems, do they exist only on Earth and only artificially made by people, or are there any natural occurring lasers or masers around? And the answer is actually yes. There is what is called the astrophysical masers out in space, in various regions of space. For example, in the atmosphere of planets, or also in molecular clouds out in space, where by interaction of the atoms and molecules with radiation that is present everywhere in space, the hyperfine and molecular levels are populated not only in the ground state but also in excited states. And then if there's just enough of these excited atoms and molecules around, then maser, like coherent emission by stimulated emission of radiation, can occur. And this is not like a very seldom, very specific thing. These astrophysical masers have been observed for many different molecules like OH, CH, and so on, ammonia, also hydrogen, of course, in space. And yeah, that's so there are natural masers, not actual optical lasers, but masers present in nature. But I mean, you may wonder, okay, I see the point that there's excited atoms and molecules around which could amplify radiation and lead to stimulated emission of radiation. But what about the resonator? What about the cavity for the feedback? So what do you think? I mean, how can these molecular or atomic clouds, how can they radiate stimulated emission if there's no optical or microwave cavity that back reflects the light through the medium? Any ideas? Please speak out if you just have an idea. Obviously, there's no microwave resonators out in space, and still we have nearly coherent stimulated emission that we can detect coming from these astrophysical objects. How does it work? Any ideas? Well, I'm not sure if this is trivial or no one has an idea, but indeed, from the laser or maser principle, yeah, we need a pump, we need a gain medium, an active medium, we need a resonator, an optical or microwave cavity. The latter, the optical cavity, is missing, but still stimulated emission can prevail. And that's just thanks to the sheer size of the system. And what happens is actually a process very similar to what is called amplified spontaneous emission, or ASE. Those familiar with dye lasers and possibly also fiber lasers are maybe familiar with ASE. In those laser systems, this is typically something you want to avoid in the astrophysical system. ASE is what creates stimulated emission, and what happens is that just in this hugely extended cloud of atoms or molecules, a first spontaneously emitted seed photon, it's called, a photon that by spontaneous emission happens to travel along the, let's say, the most extended axis of this cloud of atoms or molecules, then has a chance to hit another atom to drive a stimulated process, producing a second photon. Then these photons would again hit another atom or molecule, and eventually a whole avalanche cascade of these stimulated photons is emitted, and we produce radiation, which is dominated by stimulated emission, although it is not perfectly coherent because still it is initiated by an initial spontaneous seed photon, which just gets amplified along the large extension of the gain medium. So this is a process that, again, is very general. It happens in these astrophysical masers. It happens in dye lasers. If the feedback, if the resonator is misaligned, for example, or the mirrors have bad reflectivity so that the feedback is bad. But we will see that this is actually a very important process also for XFELs. And the reason is that in the X-ray region, obviously it's very hard to to build an optical cavity, because there are just no materials that have high reflectivity in the X-ray region. So that most XFELs nowadays actually rely on exactly this this gain process. In an FAL, it's not called ASE, that would be called SASE, SASE, self-amplification by spontaneous emission, but the main process is the same. Yeah, it's an amplification of spontaneous emission along just one pass through the gain medium. Okay, let's now get actually into a little bit more into the details of the actual laser mechanism. How are we doing with time, Shiva? Please tell me how long we should continue and when to stop and continue tomorrow. If not, then maybe we could still proceed with this. This is a very nice simulation. Let's try to get this simulation up and running. Shiva, if you're online, please can you tell me if the simulation works? If you can see my screen. Can anybody give me feedback whether
It's working.
it's working? Okay. So this is a nice, I highly recommend that you play around with this if you want to get some, let's say, hands-on, online hands-on experience on how to make a laser. Let's jump to the laser right away. So this simulates how laser activity works. So we have a medium that is filled with atoms in different levels. There's levels 1, 2, 3. And now, and we want to make the system laze. So first thing to start the lasing is obviously we have to switch on the pump and energize the system. So let's switch on the pump, which is represented by a set of lamps here. The pump radiation does not have to be coherent, can be any kind of lamp or flash lamp or whatever, just good enough that it drives the transition from level 1 to level 3, where level 3 is the upper lifetime, the upper laser level. And you can see that these little balls represent population in the upper level here. That's actually the upper pump level. Just below is level 2, which is the so-called upper laser level. And then we have one common ground state in this system. So by turning on the pump, we energize the system, we pump the atoms into level 3, and from level 3, very quickly, the atoms can decay into level 2. Actually, the decay rate we can adjust here and tune from short lifetime to long lifetime. You can see if the lifetime is short, then there's almost no population accumulating in the upper pump level, and the population immediately decays or relaxes into the level 2. And that is actually obviously favorable, because what we want to drive the laser transition is population inversion, right? We want many atoms in the upper laser level and only few atoms in the lower laser level, so that stimulated emission will dominate. And now the question to you. So obviously the lifetime of the level 3 should be short, because we want to have the atoms decay into level 2. What about the lifetime of level 2? Should it be short, such that the population quickly relaxes into the ground state, or should the lifetime be long, such that population accumulates in level 2? Please tell me. And then at home. Yeah, sorry, please go ahead.
It should be long.
Why?
because you want stimulated emission.
Yes, we want, and I mean, we want population inversion. Yeah, we want what's called an inverted distribution of population, where there's more atoms in the upper laser level 2 than in the lower level 1, so that stimulated emission can occur and will dominate over absorption. You're exactly right. Okay, so this seems to be a good choice of parameters now, but still we don't have any laser power. So what is missing? What do we have to do to actually make this system laze as a real laser? I mean, you can see that sometimes the internal, what is called internal power here, the laser power sometimes like fluctuates a little bit up, meaning that there is actually some stimulated emission coming out. This is exactly here now. You can see there's some stimulated emission. This is exactly this super radiance or ASE, amplified spontaneous emission happening, but this is not actual laser radiation. So what do we have to do now to make this a full-fledged laser?
Population inversion.
We have population inversion.
Um,
See how much population is in the level 2, much
And
more
yeah.
than in the laser in level 1. So there we
enable
are well
mirrors.
set. Sorry?
Enable mirrors.
Yes, we need the resonator, the optical cavity. So let's enable the mirrors. And we can even control the reflectivity. The reflectivity is, if we put it high, then you can see the red photons are now the laser photons that are emitted on the 1 to 2 transition. And the red photons are now reflected back and forth. And yes, now you see we have lasing. There is lots of stimulated emission and many more photons being created. And almost no beam coming out. So is this the right way of building a laser? We have very strong stimulated emission happening inside the resonator. Oh, now it's getting dangerous. Wait, maybe we should reduce the pumping. We are reaching the, in this simulation, you can actually blow up the laser. The laser has blown up. Yeah, too much power inside. So we have to restart the system. So we had high intensity inside the laser resonator, but almost no beam coming out. What's the problem? What should we do to get a laser beam out?
Reduce the reflectivity of the mirror.
Yes, correct. Okay, how far? Should I put it to 0? Is that a good idea?
Not
No. So which value should I choose?
50% approximately.
Let's try 50%. Yeah, might be not actually not so great, right? There's the laser power has dropped again. How about, yeah, okay. I mean, the point is there is some optimum, which typically, depending on how strong the gain is, how long the gain medium is, and so on, the reflectivity of the outcoupling mirror that outcouples the beam should be on the order of something between maybe 60% and 99%. Let me just put 84 or so. And you can see that now we have strong laser activity going on inside the resonator and still also lots of photons coming out to produce a laser beam. Okay, maybe we can even afford to reduce the reflectivity to outcouple more light. Yeah, actually we should outcouple more light, otherwise the intensity again gets too high and we would, this seems to be good conditions, right? 60%, 64%. Now we have a really strong laser beam coming out. Anyway, so this is fun to play around with, and it's really gives you a good idea of how laser physics works. So let's go back to our laser basics. Yes, so this is just to highlight that the laser cavity actually is important, and the main function is that that it feeds back the stimulated emitted light into the gain medium, and then thereby enhances more stimulated emission and helps us to beat the enemy, where the enemy is spontaneous emission, right? So definitely we need a cavity for real to get a real and intense laser beam. Now I mean, it's getting past 3 o'clock. Shiva, what do you say? How long should we continue?
Hi, Marcel. We can continue if you like for even another half an hour. It should be okay.
Okay.
Yeah.
Then yes, then let's continue. So then I wanted to quickly go through the simplest, most description of the laser system of lasing using what is called the rate equation model. And that actually is very instructive to also understand how the spectrum of laser emitted radiation looks like. So I assume that all of you have heard about rate equations to describe laser activity, but this is a fast recap and trying to get to the essential result as quickly as possible. So what's shown to the left is the most efficient level scheme that basically all lasers, conventional lasers are built upon, which is the so-called 4-level laser, which has the level 0, that's the lower pump level. There's a level 3, that's the upper pump level. So the pump transition goes from 0 to 3. Then there's a very fast decay or relaxation into the upper laser level number 2, and laser transition between 2 and 1, where stimulated emission is driven by, in this notation, it's the Einstein B coefficient. Remember, that's the coefficient that controls stimulated emission, also absorption. And then we have to multiply by the photon energy and then times the photon density, which is the external field that drives the stimulated emission rate. And we have our enemy, the competing channel, which is the stimulated emission. Sorry, the spontaneous emission, yeah, which is given by the spontaneous emission rate constant Einstein A coefficient. And so the simplest rate equation model to then really simulate how this scheme works is based on what is called the inversion. So inversion is just the difference in population in the level 2 minus level 1. And for the rate of change of inversion, we have these 3 terms. We have a positive change, meaning we build up inversion by pumping the system, obviously. By pumping population from the lower level up in level 3 and then quickly decaying into level 2, this enhances inversion. So that's this term. So it's proportional to the pump rate times, as in an approximation, the total population of the system, if we assume that most of the population always is in the lowest state, which is for CW lasers, this is actually a good approximation. Then we have 2 terms that deplete the inversion. So one is the depletion rate that we want. Yeah, that's the stimulated emission given by the Einstein B coefficient driven by the photon density, but the density of photons that we want to get out. And of course, proportional to how much inversion there is in the first place. And we have our enemy, which is this spontaneous emission that's proportional to the number, to the inversion that we have, times the spontaneous emission coefficient, the Einstein A coefficient. The second variable in this rate equation model is the photon density. Yeah, so inversion describes the active medium, which couples to the light field, and the light field is described by the photon density, which couples back to the active medium, to the inversion, through this this set of coupled rate equations. And the photon density, the rate of change of photon density, of course, is given by exactly the same term, the stimulated emission term, which here is positive because stimulated emission enhances photon emission and photon density. So there's a plus. But there is an extra depletion term, a term that reduces photon density, which is proportional to how many photons there are. And then there's given by like times the decay rate, which is 1 over the photon lifetime. And that is mainly given by the reflectivity of the mirror. If the reflectivity is low, we have a short lifetime. Photons fly out of the resonator, so the lifetime will be short. And yeah, this two terms, can be also interpreted as photon density times the gain. Yeah, the gain is the amplification by stimulated emission through the gain medium minus the losses of photons out of the resonator. So obviously, the condition for lasing is that the gain has to be at least equal to the losses, ideally even larger, to enhance lasing. And if we plug in these two terms, so gain is this stimulated emission term, and that has to be at least equal to the loss rate, which is given by the photon lifetime, then we can convert this or isolate for I. This I is 1 over h bar omega times Einstein B times photon lifetime. This is called the threshold inversion. So we need to produce this, reach this threshold value for the inversion to actually have any lasing going on. Otherwise, if the inversion is below that, then the gain would be lower than the losses, and we would not be able to have any lasing starting. Then the next consideration is what condition do we have to fulfill for what CW lasing? CW lasing means both time derivatives have to be 0, where we want steady state conditions, no change in time. So we set dp by dt equals 0. And that essentially, setting this equals 0, there's a p here and a p here, which can be p times gain minus loss. Setting equals to 0 means either p is 0, okay, this means there is no lasing, or gain equals losses, and gain equals losses means the inversion just equals the threshold inversion. So this means that in CW lasing, the inversion is always locked to just the threshold value. And that is actually quite an interesting or a result you have to think about for a moment, because it means that even if you pump the system strongly by enhancing the pump rate here and like pumping population up into the upper laser level like crazy, still the inversion, so the difference in population between level 2 and 1, will be just locked to the minimal threshold value that is needed to obtain lasing. And what that means, here I wanted to quickly draw what that means in terms of spectral response is, let me make a little drawing here. Now I'm plotting the laser activity as a function of the photon energy, of the frequency of the light. So in the laser, there's various components that determine the frequency behavior. One is the laser resonators, laser resonator modes. Yeah, for the light to resonate inside the laser cavity, the wavelength has to fulfill the resonance condition. And the resonance condition, maybe somebody remembers what the resonance condition, like how we can formulate the resonance condition and what this has as a consequence for the spectral properties of the laser resonator. So what I'm drawing here is the so-called resonator modes. And the resonator modes, this is just like the periodic pattern of the transition of the transmission maxima of the laser resonator. That's basically where the frequencies at which the resonance conditions are fulfilled, where this standing wave is present in the laser resonator. Does anybody remember what the spacing between the resonator modes is for a cavity that has a length of a cavity length of L, let's say?
C by 2NL.
Sorry, say again?
C by 2NL. Oh, those are the number of modes.
Sorry, I didn't understand exactly. E by, can you say again?
C by 2NL.
So it's like the spacing between resonator modes is just given by C divided by 2L, where L is the length of the resonator.
Oh.
This just comes from the condition that that the resonator length, like inside the resonator, you can have only integer multiples of half the wavelength of the light. Yeah, so just transform this resonance condition. So n times lambda over 2 equals L can be transformed into frequency modes, and then this should be nu instead of omega, but okay. And then we get a spacing between the resonator modes of C by 2L. Okay, that's the resonator. Then let's see what other spectral properties we have. We have also the gain medium. Yeah, basically the width of the gain profile, which is essentially the width of the transition. So here the spectral width of the transition between level 1 and level 2. I exaggerated a bit. It's very broad, but in many systems, this can be quite a broad transition. And so this is gain. Let's call it G, or like gain. And there is one more quantity that also has a spectral dependence that is important here, and that is the loss curve. Obviously, like the reflectivity of the mirrors. Let's change the shape here, the color. Obviously, the so loss is red, gain is blue. Obviously, the loss curve, the resonator mirrors have some spectral dependence, and the losses are high if the frequency is way out of the range. So then the losses shoot up to the left and to the right. So in which range can we have lasing now? At which frequencies can we have lasing in this graph here?
Where the gain is more than loss.
Yes, correct. Yeah, I mean, that is the fundamental condition was gain is larger or equal than losses. That's exactly represented here. We have the blue curve is larger than the red curve in this. So essentially, but I mean, can it laze everywhere between these crossing points? No, it can laze only at the on the resonances of the resonator. So basically only around the peaks of these resonator modes. But so but there's one more thing that we just learned in the last slide. We learned that in CW lasing, the inversion, and the inversion is proportional to the gain, is locked to the threshold inversion, meaning that the gain reaches or never exceeds the loss curve in CW lasing operation. So this situation, as it's shown here, obviously is not the situation when the laser is actually lasing in CW. This situation is the case when, for example, we are blocking laser activity. We are just pumping the gain medium. A large gain builds up, but lasing does not occur. Because if lasing would occur, then what would happen is that, just as we have just seen, when lasing occurs, then the gain is reduced down to the condition gain equals losses in CW mode. And that has to happen exactly at one of the laser modes, right? Because only at the laser mode, like at the resonance, we can have a standing wave and lasing can occur. So this here, this would be, let's say, let's call it, let's make it like this. This is now lasing in like what is called the saturated gain. Yeah, that is to saturated gain. That's the gain under laser activity, like CW laser activity. Now the question to you, if we now want to plot down on this bottom panel, what is now actually the spectrum of the emitted laser light in CW mode? So we have saturated gain, yeah, it is lasing in CW mode. The gain is reduced to gain equals losses, at least at that one point where also a laser mode is present, so that the resonance conditions is fulfilled. What is now the spectrum of the emitted laser light? So if we now if we plot here P of omega on that one here. So this is the P laser, the output power as a function of frequency. What's the spectrum? At what photon and at what frequencies is there laser activity? Is there laser light present? So let's say, let's see, is it, so can we have laser activity here?
No.
No. because okay, for very simple, we are just in the middle between two laser modes, so this doesn't work at all. Okay, how about we are here, just right on this laser mode. So resonance condition would be fulfilled, but does it in CW mode, does it lays here?
No.
No, because the loss is larger. Here we have loss is larger than gain. So there is no, so the only frequency where actually the gain just equals the losses, so where just the laser condition is fulfilled, both in terms of gain larger or equal losses and in terms of that the frequency matches one of the laser modes, is there's only this one point in the frequency spectrum, right? So the laser output spectrum that we expect from this model looks like this. It's a delta function. Yeah, that I don't know if you have thought about this before, but this is I always find it very very astonishing that just from this very simple rate equation model, from which we obtain gain equals losses in CW mode, of course we have the resonance condition, standing wave, and so on. From this simple model, we obtain a laser output spectrum, which is essentially produces a monochromatic single frequency line. So single frequency means like perfect monochromatic. It means an infinite sine wave in time. Is this realistic? Is it true that a laser actually has a delta-shaped frequency spectrum?
There will
Not
be a
usually.
Not usually. Why not? I mean, what limits the line width of the laser? Why is it broader if it is broader?
thermal radiative emission.
Sorry?
Radiative emission.
I mean, laser emission is radiative emission. What do you mean by radiative emission?
No radiative, thermal.
Thermal. Maybe you mean spontaneous emission. Yes, I mean, you're right. Of course, there is also some contribution of spontaneous emission because, I mean, even in this saturated gain condition, there is still gain. There is still like inversion present, like off resonant or off away from this line, right? So, and all these spectral components to the left and to the right of the delta peak can also produce a spontaneous light. And the spontaneous light does not have to match the resonance condition because the spontaneous photon can fly out in any direction even. So yes, there is some contribution of spontaneous emission. So there would be, we would expect some additional like broad base pedestal. But what about the actual like stimulated emission line, this delta function? Is it actually a delta function? Or if, I mean, obviously in reality, nothing is a delta function in real life, but what limits the line width in reality, in real life? What do you think?
Finite lifetime.
Sorry?
Finite lifetime or from the uncertainty principle. Like
Yep. But a finite lifetime of, I mean, the finite lifetime of the upper laser level, that's included in this very broad gain profile, right? So, I mean, we include the finite lifetime by admitting this broad, the broad gain profile. And we even include a finite lifetime of the photons in the laser resonator. This finite, like the photon lifetime, that determines the line width of the resonator modes. Even that is included, and yet by this simple model, we expect this very sharp line.
Cause vibration of the cavity.
Yes, exactly. I mean, in real laser systems, mostly it's technical noise. It's, as you say, vibrations of the mirrors. It's fluctuations in the gain medium because, I mean, any gain is pumped by some flash lamp or like, I don't know, a lamp or an injection current or discharge, which always induces noise. So the gain profile moves up and down and left and right. So it's mostly technical noise sources which limit the line width. But the point is, if we make everything right, we limit technical noise, then actually the laser line width can be made extremely narrow, much narrower than even the gain profile and even the resonator modes, just from this basic principle of lasing. And yeah, I mean, I'm dwelling on that a little bit because we will see later on when it comes to XFELs that there is also schemes nowadays where even XFELs can be made to lase in this way using an optical cavity, and then the hallmark of feedback lasing is this formation of a very narrow emission line of the laser, and that comes out already from this very simple rate equation model here. Okay, I think time is up for today. There's plenty of time tomorrow and the next weeks to continue. So the next topic would be then to talk about the second element in lasers, which is mirrors, which is another challenge for creating an X-ray laser, because essentially there are no mirrors that have high reflectivity in the X-ray range. So the question is, how can we yet make the laser lace even with no high reflective mirrors? And underway, we will discuss a few other types of X-ray light sources that we should consider as alternative light sources for XFELs. Okay, yeah, thank you for today. We meet again tomorrow and continue with these simple considerations about laser physics, and then tomorrow we will get to also the basics of synchrotron radiation to get prepared for XFEL radiation. Thank you.
Thank you very much.